right. I think we left off here. All right, so I think we left off here. We had homework, right? As you do, pick this up, modified it, updated it. So I asked you to do part A, which is, are you doing a t-test or a z-test for each of these? And you should find now, I think I only had maybe one person ask, how do we hand it in? Maybe two. Now you find out. So under the homework folder, there should now be this quiz, homework number 9, T or a z-test. So you've got 5 minutes. Open that up, and it is same questions 1 through 5, and just state if it's a multiple choice. You just click either t-test or a z-test. Okay. They are. Should be. Pretty certain. In 5 minutes. No, they are not in order. Why are they not in order? Oh, I know why they're not in order. Let me get, but yeah. Well, if you've already started, we'll just leave. Yeah. Sorry, that was. Second question is actually at the end of everything else. Again, under the homework folder, you'll find a quiz. It's a t-test or a z-test. like we have it. All right, cool. We're gonna probably do more of these. We can do it. Kind of add some quiz grades. Prep for the exam. But let's go through this. One sample test. All right, so first one. All right, so what are we looking for? When we have our decision between a z-test and a t-test, what are we looking for?
Sample standard deviation versus population.
Yep, we are looking for the sample standard deviation versus the population standard deviation. If we have a sample standard deviation, what are we going to use? T-test. If we have a population standard deviation, what do we use? Z-test. All right, that's what we're looking for. That's it. So question one, in 1998, typing speed of all computer users was 33 words per minute with a standard deviation of 5 words per minute. An individual has a typing speed of 25 words per minute. Is this individual different from the population average? Is this a t-test or a z-test, and why? Z-test, why?
33 words per minute of all.
Okay.
Deviation of 5.
All right, so that's population. Yep, so we defined our population as that all computer users in 1998. And from that, we have our population mean, that's mu, and we have our population standard deviation, sigma. All right, number 2, Braga. One species has a mean length of 23 millimeters. We have 7 samples. Mean standard deviation of the sample is 20 and 2. So, is this a t-test or a z-test? Z-test. Why? Yeah, so which one's our population? That. One species. We've defined the species. The species itself is the population, which consists of all individuals. Oops. Did you hear that crunch? I don't think he was dead yet. Anyways, that all individuals of that species represent our population, and then we have a sample of 7, which we're determining are these actually in that part of the population. So from that sample, we have our mean and our standard deviation. We don't have a population. So that's a t-test. Question 3, we have an average grade for a course, and then we find one paper on the floor with an average. So this is a z-test or a t-test. T-test. Did you say t-test? Why a t-test? Do we? What's our population? Population is all individuals who have taken course A. So that's our population. Our sample is a single paper that was found on the floor. So our course A, give you 71, that's our average, and then also sigma. So the other aspect of this is if you see sigma, you know right away that that's our population. So if we have a population of sigma, which one do we use? Z-test. Z-test. All right, and that is opposite of number 4. So final exam has an average of 114 minutes to complete. So this is out of all individuals that have taken the final exam. So that's our population. And then we have a sample of 18 with a mean of 95, standard variance of 40. So t-test or a z-test? Hopefully say t-test because we're working with our sample. I give you an S or an S squared. That's our sample. That clues us in then that we're using a t-test on this one. Then, number 5, average height of American men. So this is our population. We have a sample of 12 men with an average height and a sample standard deviation. So a t-test or z-test. That's our t-test because we have an S. So in some of these problems, you have to actually ask yourself, what's our population? That's like number 1 and 2. What's our population? Was the standard deviation given for the population or was it given for the actual sample? And then you have second type of questions where I give you sigma or S squared or sigma squared, but you have the actual value. So you don't really need to figure out which one's the population, which one's the sample, because I told it to you using the variables, using sigma or using S. And again, if we have sigma, that's our population, we do a z-test. If we have S, that's our sample, we do a t-test. So z-test for population, t-test for samples. All right, so now you should be able to, you know, what test to run. Now you can do this, perform the test and answer the question. All right, so what I'll do is I'll probably get this uploaded, or made as an RMD file. So then you can do it in R and just upload it. All right, okay. That'll give you time today. I think we'll make it due on Wednesday. So other thing today is that in lab we will take our exam number 2 closed book portion, kind of like a redo, you can say. So we'll have probably a little bit of lecture, and then what we'll do is you have 60 minutes total from the time when you started to when it's done. It's 60 minutes. All right, we have to do it here in the class. So what we'll probably do is we'll finish up our lecture, I don't know, probably by about 2:30, 2:40. And if you want to take a 5-minute break, you could, and then come back. I think it's going to go live at about 2:45. So that way, if you want to start at 2:45 and be done by 3:45, you can. All right, and if you get done early and you hit submit, you're done. Oh, yep.
We're doing this one on.
It's online. Yep. But we'll do it here. So yeah, we'll have the z-test and the z tables and the t tables. All right, you'll have those. Bring a calculator. Bring piece of scratch paper, because you're not going to show your work. You'll do your work on a separate piece of paper, and then you type in your answer. All right, there is a total of 40 points on there, and we'll scale it to 50 points. So then what we'll do is we'll take the highest grade of either this online version versus the actual hard copy version that we did. Take the highest grade, and that'll count towards our exam 2 grade. All right. All right, that's today. So let's pick up this t-test. All right. So up to this point, we've assumed that all of our assumptions are met. All right. So if all of our assumptions are met, then our test statistic, that t observed that we calculate, will follow a t distribution with degrees of freedom n minus 1. All right, and our assumptions are that data are random and independent, and usually we're going to plan for this as we design our experiment. All right, but then the second part is that they're normally distributed, and we can't really plan for it because we don't know if we're going to obtain normally distributed data. So one of the first things we'll have to do before we run these t-tests is to check normality. All right, so if we're normally distributed, we're good. All right, our test statistic will follow a t-distribution. But if we're not normally distributed, then what happens? Well, if we don't follow normality, then our t observed will not follow a t distribution. It's going to be different, all right, skewed in some way. What we'll say. And if we're skewed in some way, then that means that our p-value is going to be wrong. So take this, for example. We have a sample that's skewed. Say that's our sample. And we wanted to run a t-test to see if our mean is equal to some value. Well, if I calculate a t-observed value from these skewed samples, and this represents a random set, a random collection, what do we notice about our distribution? So the blue is a t-distribution curve, all right? But we see our histograms. What does our histogram look like? Does that look like it follows a t-distribution? Does that look like it follows a t-distribution? No, hopefully you're seeing that it actually looks skewed. We've got too many points on the lower half and not enough points on the upper half of our distribution. And this is going to screw up our p-values, because our p-values were area under the curves. So in this case, if we're down here in the negative and we're looking for the area to the left of our point, So here's where our cursor, let's do a pin. Let's say our t observed, we came up with a t observed value right there, and we're looking for the area to the left. Well, the area to the left of that t distribution is going to give us a p-value that's lower than what it actually is. And the reason it's lower is because we're assuming it follows a t distribution, but our actual data, our actual test statistic is not a t distribution. It's shifted. It's shifted in some way. Just like if we had a t value up here and we calculated area under the curve, all right, the area under the curve is going to give us a larger p-value than what the underlying data would have predicted. So if our p-values differ, it's larger or smaller, what's that going to do to our conclusion? Well, it could change our conclusions. We may be rejecting our null hypothesis when we shouldn't, or we could be failing to reject our hypothesis when it actually should, or when failing to reject when we should reject it. So fortunately, as our sample size goes up, our t observed starts to approach normality, all right, even if we are skewed. So benefits of a large sample size, it ends up helping us get to normality and avoid some of these problems. So what do we do when we want to run a t-test? We have to check normality. How do we check normality? We've covered it. All right? So our question starts out as, are the data normally distributed? Well, we've got graphical tests or we've got a statistical test. All right, and just quick overview. Graphical tests are going to be preferred. All right. We can do a histogram with an overlay of the normal curve. That's definitely not preferred. All right. But we can do it and kind of look at the data just to make sure we've entered our data correctly. Sometimes the histogram will show us what type of skew we have, if we're skewed left versus skewed right. All right. But we need to have a suitable sample size so that we have sufficient number of bins. So if we look at pond 1 data, which we did, this was like an overview of how to do it. We've got pond 1, different number of breaks. Does it look like it's normally distributed? It's tough to tell. This is probably the best one that we could use. And again, it's just kind of arbitrary. So that would be pond 1, and I give the code. But again, we've done this. We've already had an exam on it. So we're not going to spend much time. Method that's preferred is a QQ plot. QQ plot works with smaller sample sizes, or at least it allows us to assess normality. With smaller sample sizes, it allows us to assess normality. With big sample sizes, now it is an assessment, so we don't get a p-value from it, but it is pretty good and it's acceptable. So just with our QQ plot, it's in the CAR package. And as a quick review, we're looking at making sure that all of our points fall within a 95% confidence envelope. Now, this was pond 1. All right, it looks pretty good. We do allow some of these points out at the very end, the extreme values, to fall outside, but we don't allow any points in the middle or the bulk of the distribution. All of these points in the middle need to fall on that line or within our envelope. If, however, someone says we need a p-value, run Shapiro's test. All right, so again, my recommendation, avoid using it. Just use QQ plot. So we already looked at pond 1. Pond 1 looks good. It's normally distributed. All right, so that means that whatever our conclusion was when we ran our t-test last week, get this, whenever we ran that t-test on pond 1, we can trust our conclusions. So that's, I'm getting my RStudio open. So we did, here it is, pond 1. This was our conclusion. We know that our data are normally distributed, so this can be trusted. Yes, we're confident now that the mean of these mosquito fish in pond 1 is not equal to 24.5. So ponds 2, 3, and 4, check normality for them and see which ones, if any, violated our normality assumption. And I think I said do all 3 as a review. We're just going to focus on our QQ plots. All right? We'll see which ones are normally distributed and which ones are not. All right, did you get them? So, I'm going to go through this. QQ plot, pond 2. What do you think? Normally distributed? Yeah, I think so. Data are normally distributed. Looks good. Face that. Pond 3, what do you think?
Yep.
Yep. Looks good. Pond 4. Yeah, looks good. So all of our ponds are normally distributed, which means we can have faith that our t-test actually gave us some good answers. Now, it doesn't mean we didn't make a mistake, right? It doesn't mean that we didn't commit one of those type 1 or type 2 errors, right? But we know that when we ran our t-test, yeah, we didn't have the assumptions that through, or we didn't have a t observed that did not follow a t distribution. So here's a quick assumption review. I kind of put these up. So we had our t-test. Assumptions, data are random and independent. We don't have a check. Actually, we do. There is a way to check for correlation, autocorrelation, but we're not going to learn that. We don't even learn that in the grad class, so we'll say there's no check. Instead, we design our experiment to try to satisfy this assumption. We try to design our data, or design our experiments so that we have a random sample, and then each sample is independent. All right. Second assumption is that data are normally distributed. We use a QQ plot for this, and then we've got this big part here. So if the data are normally distributed, then our t observed follows that t distribution with the degrees of freedom n-1. If the data are not normally distributed, then our t observed will not follow this t distribution. Therefore, our p-value will be wrong, and we can make a wrong conclusion about the data. So that's kind of the whole reason. And this will apply to all of our statistical tests. If we do not make an assumption, then our p-value can be wrong. We can make a wrong conclusion. Yep.
I have an error.
Uh-oh. Which error? What's it say?
I didn't vote live.
Did you capitalize include one?
There we go. Actually, all right. Not terrible. Still getting it?
Let me take a picture of it.
Oh, it don't matter. I'd rather have you hatless because you could use these as a study guide. I don't know. Some of you probably know, but we have those students at the honors conference. They're stuck in Orlando. Flight cancellations. Looks like they can fly to Dallas tomorrow, but they can't fly home until Wednesday.
Where were they going?
The NPR was reporting that it was bad weather and staffing shortages. I looked at the bad weather and I'm thinking we had like rain and maybe the Northeast, and that's about it. But they mentioned high winds in Dallas, which I guess high winds.
Yeah, when I get Dallas. This Florida without weather is unheard of.
Well, I think it was Dallas, but I think the news this morning was saying it was Dallas that set things back. They were on the standby list, but
As long as they couldn't get a flight ticket.
well, let's see here. School's pending, so you gotta remember that. Besides, they get extra days down at Orlando.
Right?
Right.
Much worse places to be stuck.
They have both flights.
Imagine you're gonna get those images of this class on live stream, and they're sitting. You see the pool and the margarita, with the little umbrella hats right next to it. Which we drove back from Rockwell on Saturday, and we saw a plane crash. It had just happened. We drove by it. It's right up.
Little plane.
Yeah, it was a Cessna. Apparently, the news, they said it lost power and then hit utility pole coming down. So in the news, they had 4 people were up walking around from it, and they had one that waited for the first responders. It was absolutely crazy how many of them were going. As we drove by, I saw like the smoke coming up. It's like, oh, there must have been an accident. And it was the tail of the planes we saw. Holy cow, it's crazy. All right, so we already did this. All right, were any of the assumptions violated? Nope. So how does that affect the conclusions? It doesn't. Our assumptions were met. So whatever conclusions we made about those ponds, hey, that works. Now, what happens when we violate the assumptions? So we know that if we violate the assumptions, our t observed doesn't follow that t distribution, and thus we can't use that t distribution to get a p-value. All right, so what can we do? Well, we've got basically 2 different types of options. One option is to perform a nonparametric test. So these are tests that don't make that assumption about a t distribution. They have some assumptions. They usually have other assumptions tied to it, but we don't make the assumption of normality and then following the t. So the 2 nonparametric tests that we can run is a Wilcoxon sign rank test or a sign test. All right. both of these, since they're non-parametric, they're going to take our data, like our measurement data, and they're going to change them to ranks. So we're going to lose information about magnitude of differences because we're not going to test those differences. We're actually just going to test like ordering. We have less power, so if we don't detect a difference, it could be due to the fact that we don't have the power to detect that difference. Now, the two tests, Wilcoxon signed rank test is probably the one that is the worst of these two. All right, it requires symmetry around the median. All right, it requires basically you pick your median values and you're going to have mirror images on both sides, the lower values and the upper values. I say this isn't recommended because normally if we violate our normality assumption, it's a violation in skew. We have skewed data, which then by definition says that we're not symmetric around that median. So anytime we're skewed, which is going to be most of the time, this is going to be a very bad test. That leaves us with an alternate test, which is the sign test. This still tests the medians. All right, so it tests if the medians are equal to some hypothesized value, but it does so by counting up how many values are greater than a hypothesized mean or median and how many values are less than a hypothesized median. All right, this works. I mean, it assumes random and independent samples, and that's about it. But we do have a restriction that we need at least 6 samples. All right, we have to have a sample size of at least 6. I say it's greater than 5. And the reason, the way it calculates p-value, if we only have 5 or less, we will never obtain a p-value that's less than 0.05. So if we have a sample size of 6, we can get a significant p-value. It's only one time, but that's what it is. These options can work. They're easy. Sign test is fairly easy. We'll work through that. The preferred method for me is to utilize bootstrapping. All right, so this is a randomization method. It makes no assumptions about our underlying distribution because what we're going to do with that, with our data, is generate our own null distribution. And you're going to see how we do that. So with our bootstrapping, we've got 2 different things. One, do bootstrap 95% confidence interval. I have that asterisk because that's going to be the preferred method. With our confidence intervals, we look, does our confidence interval capture that hypothesized median or hypothesized mean? If it does, then our sample mean equals that hypothesized mean. If our confidence interval does not capture that hypothesized mean, then we conclude that they're not equal. Easy to calculate, easy to interpret. I'm actually going to give you a function now that calculates this for you. All right, pretty easy. Downside, no p-values. Some people really need to see a p-value. That's a downside. There's also a bootstrap t-test. So we're going to learn how to do like a randomized ANOVA. And we're going to learn how to do randomized 2-sample t-tests. Well, there's an equivalent called the bootstrap t-test, the bootstrapped 1-sample t-test. It only makes the assumption that the data are random and independent, which again, we plan for as we design our experiment. And then what we get is a bootstrapped t-value. So we get a t-distribution from all of these random samples that will reflect the underlying distribution, and that's what we use to calculate our p-value. But in order to run this, we have to ensure that our null hypothesis is true when we generate all of those randomized samples. So one of the things we're going to have to do is basically subtract our mean to get everything centered or to get everything equal, all of our randomized samples equal to that value, and then we do our bootstrapping. It's an extra step, extra 2 steps, I believe. All right, we can do it, but we're not going to do it in the class. We're going to work on the bootstrap confidence intervals. So let's learn these. We're going to start with the sign test. All right, so we were going to do these with ponds. So even though all of our assumptions are met, we're going to use pond 1, 2, and 3 on all of these. So you can see that whatever we get from the t-test will be the same as what we get from all of these non-parametric tests. All right, so we're going to test if the median of a sample equals some hypothesized mean, or some hypothesized value. This is different than our t-test. Our t-test is asking if our sample mean equals some hypothesized value. This is our median. All right, so what we're going to do
is we're going to look at each of our values and we're going to convert our values to either above that median or that hypothesized value or below that hypothesized value. If we're actually equal to it, we key it as a 0 and it doesn't get counted in our data. All right, the assumptions, we already said data are random and independent, and we need more than 5. And then once we check this, then we're going to run what's called a binomial test. And the binomial test has this hypothesis, these hypotheses, which is our proportion of positives, so the proportion of our points above our hypothesized value is 50%. And our alternate is that it's not equal to 50%. All right, so let me go up to the board and show you how we're going to do it. So let's generate some data. So we're going to get our sign test, start this out, and we're going to generate some data that we can use, and then I can kind of show you how we do it, work through it by hand. Hopefully it starts making some sense. So the sign test, non-parametric version of a one sample t-test. The difference, big difference, I'm going to highlight, make that big. The big difference is that we are testing the median and not the mean. Procedure, what I guess we should say assumptions. We need 1, data are random and independent, and number 2, we need a sample size of at least 6. So our procedure will be convert. Actually, no, we have our assumptions. I guess above assumptions, we need hypotheses. All right, so our null hypothesis is that our median equals some value. And our alternate here is that the median is not equal to some value. We can also do direction on this. So if we think our data points are larger, we can do that. We can specify a direction. So we're going to convert our data to plus or minuses. So minus, plus, and 0. All right. So we're going to we lose our information about magnitude. That's our non-parametric part, and that's why we lose power. So this is why we lose power. And then once we have that, we run a binomial test to see if the proportion of plus and minus are equal. So we're going to run a binomial test to see if the proportion of plus and minuses are equal. So if they're equal, then that means that our median equals that hypothesized value, because our median marks the 50% point, right? So if our values are equal, then we've got the same number of points above, the same number of points below, and that's our hypothesized value is the median. If we have an unequal number of pluses and minuses, then we've got an excess either above the median or an excess below the median, and thus we can conclude then that our sample, our median, is not equal to that value. So, example data. All right, let's run. We are going to I'm going to call it DAT1. We're going to round an R norm. Let's give it
10 values. We're going to do 10. We'll specify a mean of 10 and a standard deviation of 3. And I'm going to round to just the whole numbers just to make it a little bit easier. And actually, let's set our seed so that when we come back, we'll get the same numbers. Give me a number. Alex. 12. Set the seed for 12. Oops. And then I'm going to view this. All right. And I'm going to sort just so I got it from smallest to largest. So here's our example data set. So we're going to ask the question, is our sample median equal to 10? So we drew our random sample from a normal distribution that should have a mean of 10. All right, and if it's normally distributed, then our mean and the medians should be equal or close to equal. So we'll ask, is our sample median equal to 10? We will assume that we violate normality. I don't know if we did or not. Right. So we're going to assume that we violated normality so that we can run this test. I'm just going to check it real quick. Yeah, small sample size. No, I mean, it's all, I'd say it looks normally distributed, but we'll just make that assumption that we violate normality so that we can run the test. All right. So we're up to this point. What we'll do is we'll come back in lab, we'll work through this. I'll actually do it up on the board, show you conceptually how this works, and then I have a script that will do this for us. All right. I have a script that'll do this for us. So let's take a break, go to lunch, come on back. Yep.
Will you scroll all the way back up to review, calculate, verify?
To do what?
To the review and type.
Where at? Here?
It's further.
Or the slide?
No, that one.
This one? Oh yeah.